All right, let's jump right into this shift briefing. Listen up, everyone, because today we're covering the exact step-by-step checklist to keep our DC motors alive and spinning. Welcome to this explainer. I'm going to walk you through the definitive guide to DC motor and armature maintenance. Now, for you junior techs just joining the floor, you know these motors are the absolute workhorses of our operation, right? They transfer electrical energy directly into rotational mechanical torque. But here's the catch. They rely entirely on parts that are literally designed to wear out. The brushes, and a rotating core, the armature. If you don't know exactly what you're looking for, a minor wear issue can and will escalate into a massive, catastrophic failure. So we're going to break down the mechanics, the symptoms, and the exact procedures you need to nail down on site.
So here's our game plan for the day. Safety protocols, visual inspection, electrical diagnostics, step-by-step repair, specs and environment, and finally, our maintenance calendar.
Starting things off with Section 1, Safety Protocols and High Voltage Isolation.
Okay, look, do not ever skip this. I mean it. The absolute very first thing you do is disconnect all power sources. But honestly, just disconnecting, that's not enough. You have to verify zero voltage at those supply terminals with your multimeter. Armature current in some of our larger motors can easily exceed 200 to 600 amps. If you accidentally make contact with an unisolated, grounded winding, you're looking at some incredibly dangerous chassis voltages. You need to follow this essential high-voltage safety isolation procedure every single time to ensure that armature is completely dead before you even think about starting your inspection.
Moving right along to Section 2, Visual Inspection, or how we diagnose by sight.
I really need you to understand why maintaining a proper graphite patina is so essential. You're going to open a motor and you'll probably see this dark chocolate brown film on the commutator. A lot of you junior techs might think, oh, that's dirt, I should scrub that off. No, stop right there. Do not do that. That film is actually a microscopic layer of carbon graphite, and it provides crucial low-friction, low-wear operation. Scrubbing it off is a massive mistake that will instantly accelerate the wear on your brushes. It's like wiping the oil off an engine part.
We actually have some really clear visual benchmarks to help you prioritize urgent armature repairs. That chocolate brown color? That means you've got a healthy patina and totally normal operation. But what if you see bright copper? Yeah, that means the film has been completely stripped, usually because of overpressure from the brush springs or some kind of chemical contamination. And if you see black burns or pitting on specific segments, back away and stop the line. That indicates severe failure, localized overheating, or internal winding faults that are causing heavy arcing.
You've got to know how to categorize these failure modes strictly into electrical versus mechanical, because that clarifies exactly how to prioritize your repairs. A tiny blue flame ring around the commutator? That's actually pretty normal. But heavy yellow-white sparking? That is a glaring electrical symptom of worn brushes, and it's often accompanied by a huge 3 to 5 volt drop across the brush contact. Now, on the mechanical side, if you're hearing a crazy chattering or rattling noise, or you physically see copper smearing and grooving on the commutator, you've got physical problems. Think brushes literally bouncing around in their holders because of weak springs or a chewed-up surface.
So the real trick is knowing the exact thresholds for when you just swap out the brushes versus when you need to actually recondition the whole commutator. You replace your carbon brushes when they're worn to 50% of their original length, or the second they hit that wear indicator line. Simple enough, right? But if you take a dial test indicator and measure that the commutator's runout exceeds 0.05 millimeters total indicator reading, or if you're seeing deep circumferential grooves worn into the copper, just slapping new brushes in won't fix a thing. You have to pull the armature and physically turn the commutator on a lathe.
Okay, Section 3, Electrical Diagnostics, Testing the Armature.
Think of this as your quick reference logic flowchart to help isolate an internal electrical winding fault from a physical, mechanical failure. If you've got an open circuit, a shorted turn, or a ground fault that keeps tripping your protection, that is an electrical winding issue. It completely disrupts the electromagnetic balance of the motor. On the flip side, a high mica condition, which is where the softer copper wears down faster than the hard mica insulation, leaving these nasty ridges, or shaft-bearing journals wearing undersize, or broken laminations, those are purely physical armature failures. Both create a highly destructive feedback loop, but you test for them in totally different ways.
So how do we find those hidden internal shorts or open circuits? Well, this is exactly how you safely run a bar-to-bar resistance test to detect winding faults across the full circumference. You take your micro-ohmmeter and you measure the resistance between each adjacent pair of commutator bars, going all the way around the circle. What you're looking for is consistency.
All of those readings should be equal, give or take a 10% tolerance. Any coil showing a wild deviation points directly to a damaged internal winding.
And then, of course, we do our insulation resistance test, also known as the Megger test. We apply 500 volts DC between all the windings and the armature core. See that 1 mega ohm mark? That is your absolute drop-dead minimum acceptable insulation resistance. If it hits exactly 1 mega ohm, you are teetering right on the brink of a dangerous ground fault. Honestly, a healthy, perfectly dry motor should easily read over 100 mega ohms.
Which brings us to Section 4, Step-by-Step Repair, Fixing the Faults.
Let's say you're just dropping in new replacement brushes. You can't just slap them in and walk away, guys. You need to memorize these correct techniques for bedding in new brushes. You want maximum contact surface without scratching up the commutator. You wrap 120 grit sandpaper around a dowel that matches the commutator's curve. Now pay attention, the abrasive side must face the brush, never ever the commutator. You pull it under the brush to seat it. You're aiming for at least 75% to 80% of that brush face making solid contact. Finally, run the motor at no load for 30 to 120 minutes to finish bedding them in before you even think about applying full industrial load. And please, never just guess on replacement parts. Always double-check that you're installing acceptable brush grades based strictly on the specific motor application. If you've got a general-purpose DC motor, you want electrographitic or EG grades. For high current, low voltage situations, you absolutely need metal graphitic or MG grades because they can handle much higher current densities. If you throw the wrong grade in there, you're going to cause rapid wear, overheating, and massive electrical instability, even if that brush is brand spanking new out of the box.
Next up, Section 5, Specs and Environment, the operating parameters.
Let's get down to the exact numbers. These are the critical specs you have to measure with your spring scales and depth gauges to guarantee standard industrial operation. Brush spring pressure? That has to sit between 150 and 400 grams per square centimeter. If it's too low, you get bouncing and arcing. Too high, and you generate rapid wear and heat. If you end up turning a commutator on a lathe, your final surface roughness has to land perfectly between R0.4 and 0.8 micrometers. Plus, you've got to use an undercutter tool to drop that mica insulation 0.5 to 1.5 millimeters below the copper surface. Otherwise, the brushes are just going to chip against it.
But listen, all those specs mean absolutely nothing if the room itself is actively killing the motor. You have to pay close attention to environmental factors, things like low humidity or nearby oil, which will instantly degrade your brushed graphite films. If the relative humidity in the plant drops below 30%, that graphite film literally breaks down and brush wear shoots up by 3 to 10 times. Or, if you're operating at altitudes over 1,000 meters, the thinner air reduces film stability, meaning you have to increase your brush spring pressure by 10 to 20% to compensate. And keep oil and grease far, far away. If even a little gets on the commutator, it destroys the film and causes rapid destructive smearing.
Finally, Section 6, Maintenance Calendar, Preventing Catastrophe. We use a strict 500-hour recurring inspection calendar based on operational hours to track brush wear and insulation health consistently. Every 250 to 500 hours, you need to visually inspect the brush length and blow out carbon dust with dry compressed air. Keep it at max 30 psi though, so you don't blast the dust deeper into the windings. At 1,000 hours, we do a full visual inspection and your 500 voltmeter test. Hit 2,000 hours, break out the dial indicator for runout measurements and run a full bar-to-bar test to catch any degradation early.
This right here is basically the golden rule of our operating manual. Ignoring minor mechanical wear will always lead to catastrophic electrical failure. Think about it. A set of replacement brushes might cost $50, but if you let them wear down to the bare pigtails, they are going to severely score the commutator. Now you have to pull the whole motor and turn it on a lathe, which costs $500. And if that excessive current ends up damaging the internal insulation, well, now you're looking at a full VPI rewind that costs thousands of dollars.
So I'm going to leave you with this question to chew on. Trending your data is your absolute best early warning system. Let's say you've got a motor that read 500 mega ohms on your Megger test 2 years ago, but today it reads just 10 mega ohms. Now, technically, it's still running, and yeah, it's above that 1 mega ohm absolute minimum. But look at the trend line. Are you really going to wait for it to catch fire? Or are you going to proactively rewind it today? Use this checklist, trust your diagnostics, and let's keep this plant running smoothly.